Hello everyone. So yes, I'm Jonathan Heathcote. I'm from BBC Research and Development, and today I'm going to tell you about some work I've been doing over the last few years, over the last year or so, looking at how we can improve the throughput of the media CDN that the BBC runs by improving the performance of the servers involved. So as a bit of background then, if you're watching iPlayer, there's a reasonable chance that the video you're receiving is coming from one of a network of servers dotted all around the UK. These servers essentially are located inside some ISP networks, some BBC data centres, and the idea is to route people to a server that's near to them. And in this talk, we're going to be focusing on these servers rather than the sort of broader structure of the CDN. And these servers essentially have a fairly simple job to do. So inside, we're using Nginx as a caching proxy, and our video streaming workload essentially is serving a half meg to 5 meg file every 4 to 8 seconds via an HTTPS request. So no video coding or anything like that going on. It's just simply a file server, which, as I say, we're acting as a cache because the library of content available through iPlayer is too big to serve out of a modest-sized server. So a very small fraction of our workload does get sent back to our origin service, but essentially relatively straightforward. Now, if you want to know more about the broader CDN structure and how all of that works, then there is a fantastic talk from UK NOF a few years back, which goes into an overview of how this works. But in this talk, as I say, we're going to be concentrating on what goes on in these servers that actually serve the media. So I'm going to be talking about a few different things. One of them is ARM servers. Spoiler, we've been trying them and they seem quite good for this workload, and I'll tell you more about that in a minute. I'm also going to tell you a little bit about the horror that is memory bandwidth, because it turns out, like in so many fields, the task of serving media out to the network is very much a memory bandwidth bottlenecked situation rather than CPU bottlenecked as it once was. So the rate at which you can get stuff in and out of memory, that's now our primary concern in many cases. And so to deal with this, I'm going to be talking about some technologies such as KTLS, where you run the encryption process inside your kernel, and also the idea of TLS offload, where you actually use your network card to do the encryption for you. And finally, I'm going to cover some of the impact that real-world network conditions have on this, and then consequently on the performance of these servers. So let's first of all get stuck into the question of these ARM servers then. So these have been emerging on the market for quite some number of years now, and the marketing materials tell you that they are slightly cheaper and use slightly less energy. So that sounded good, so I thought let's have a look at this. So got ourselves a simple test lab where we have one of these ARM-based servers, and we have a bank of other servers which are going to act as traffic generators, so emulating up to about 100,000 or so people watching iPlayer in a given moment. Now the server under test we set up with a 128-core Ampere Ultramax CPU, which honestly is something of a beast despite the amount of energy it claims to drink, along with a pair of ConnectX-6 DX network cards, giving us a total of 400 gigabits a second network connectivity, and a load of very fast NVMe disks to act as our cache storage for this application. Now, as a bit of an aside, the supporting infrastructure for this that emulates all of the other BBC services that make this CDN run, they all live off in virtualized infrastructure off to the side. And in fact, this whole test setup is deployed as part of our on-premise cloud based on OpenStack, including the bare metal machines that are doing the load testing and the system under testing itself. And for those of you who've not worked with this sort of environment before, this is really, really cool stuff that you should definitely look into, because it, for example, in our setup means that we can deploy everything from the BIOS settings all the way up to the CDN software running on top of this, all using standard cloud tools like Terraform and Ansible, which is just really nice as a sort of nice experimental environment, and gets you obviously a lot of the way to building this sort of stuff without having to do very much work. So that's a bit of an aside. So ARM servers then, are they any good, right? Get to the point. Well, the answer is really boring. Like, they look like ordinary servers. You download a disk image off your preferred Linux distribution's website, and it boots and installs the same way as any other server. All the software you expect is kind of there. Our CDN software, we'd never tried it on ARM before, so just recompiled it, and it just worked. So that's pretty boring. Luckily, there is some more interesting stuff going on here, which is that it turns out there are some architectural differences between ARM and x86 processors, your AMDs and your Intel processors, that makes it well suited for this media CDN workload. And in particular, that is the choice of page sizes that it offers. So as a bit of background for those who aren't familiar, when your operating system loads a file from disk, typically it loads it in lots of small chunks called pages, and those pages get stuck into memory as needed. Now in practice, they don't get stuck next to each other in memory, they get stuck wherever there happened to be space when you requested them. And this is all very convenient for the operating system, but if your server software underneath is trying to use it, it's no good, because now your data's all over the place, which is a bit of a disaster. So what you have to do is reassemble all of these pages that are scattered all around when you want to access them. And to do this, your processor has a little component called a TLB, or translation look-aside buffer, which essentially does this address translation for you to make it look, from your application's point of view, like you've got a nice continuous block of data rather than scattered fragments all over the place. And this is fantastic, this all works very well. The problem is these blocks are historically very, very small. So a typical page size might be 4 kilobytes. Now we're talking a few megabytes worth of data per file, so we're talking, a serious number of these things. And of course, we're not just serving one file, we're serving large numbers of files. And so very quickly we had this situation where we have absolutely loads and loads of these pages which need to be mapped into the correct order, and our TLB runs out of space and performance starts to tank, because now our processor's got to go and look up where on earth did all these things go in a much more slow and manual process. And so when this kind of thing happens, performance absolutely goes through the floor, and that's a big problem. Now there's obviously many ways you could go about tackling this problem. One of them is to put in a lot of engineering effort into working out how you can move your workload around to try and keep the number of files you're accessing from a particular CPU core, for example, down. That's one option, but it's obviously quite a lot of engineering effort to do. The other is to use larger pages, right? Because if we use larger pages, we need fewer of them, and that's going to reduce the pressure on our TLB. So unfortunately, in the world of Intel and AMD-based processors, you're limited to only 4 different page sizes. And in practice, you're not able to use the 2 megabyte or 1 gigabyte pages for your system page cache because they're just too big. All of the system software around assumes the pages are relatively small, and if you were to use something bigger, everything would start wasting memory all over the place, and essentially it's just not an option. Now, on ARM, there are a lot more options. Now, we still can't use the larger page sizes, but we now have 16 kilobyte and 64 kilobyte options, which are obviously considerably larger. Now, obviously 4 kilobytes might have made sense many, many years ago, but in the modern world with terabytes of RAM being a thing, 4 kilobytes is just so very, very small. And it's interesting to note that Apple, for example, in their new range of ARM-based processors, they default to using 16 kilobyte pages. And that helps reduce pressure from their environment. In our case, we're dealing with large numbers of very large files, so we went with the largest sensible option, which in this case is 64 kilobytes. So does it help? Yeah, it does. So on the same server hardware and the same software, just changing the system page size up from 4 kilobytes up to 64 kilobytes gets you from 80 to 150 gigabits of traffic being served off a single machine, which is obviously really nice. And the really nice thing about this is a single, setting change, not a huge re-engineering effort. Now, this is all good and well, and we've now eliminated the problem of the CPU. Unfortunately, we're now on to the big baddie, which is memory bandwidth. And this is where things start to get pretty scary. So I'm sure many of you have seen this plot many times. This is, of course, the not quite exponential rise in CPU performance as predicted by Gordon Moore. This is the more exponential, but unfortunately lower rate growth in memory throughput over that same time period. And what you can see is that over the years, CPU performance has been growing really fast and outstripping memory performance. And so it's now common in many, many fields for your workloads to be completely starved for memory access. So your CPU sitting there going, I'm ready, and there's just nothing available because the memory has just not got the capacity. So let's see how this plays out for our media CDN workload. So let's say a request comes in from the network for a bit of video. Well, the first thing we have to do is load that video from disk into memory. Fair enough. At this point, the data is living inside the operating system's address space. Now, this means that our web server, Nginx, can't access it. So the first thing we need to do is copy that from the operating system's memory space into our application's memory space, at which point we can now do our encryption process. We then, of course, have to do the reverse of copy this data out of Nginx, out of our web server, into the operating system so that it can then be sent out to the network. So this means that for every gigabit of traffic that we're delivering to people at home, we're spending 8 gigabits of memory bandwidth. Now, to put this in perspective, the servers that we're using, the data sheet will tell you it can do up to about 1.5 terabits of memory bandwidth, which sounds like a huge number. In reality, of course, it's more like a terabit or so that you can achieve under real-world workloads. But, of course, because we're spending 8 times the memory bandwidth as the network bandwidth, that means, that's only 1/8 of a terabit. And that's, of course, what we're seeing with this 150 gigabit limit that I was talking about before. So what do you do? Well, one option here is to use a technology called kernel TLS. So we move the encryption process, the TLS encryption process, out of our web server and into the kernel. Now, the kernel is not in any way better positioned to do TLS or encryption in any way. However, because this process is now running inside the kernel, we don't need to perform those memory copies because the encryption process can read directly from the disk buffers and write directly out to the network card afterwards. So this halves our memory throughput requirements for this same application. And does this work? Well, the answer is yes, again. So again, switching from doing our encryption inside the user space program to the kernel gets us up to 260 gigabits a second, which is, again, another nice win for not too much engineering effort. Now, at this point, people usually will start telling you about this idea of TLS offload. So what if we could offload this encryption process from our processor instead into our network card? Now, obviously, that's very nice. Our network card, this is very nice. Obviously, now our CPU is completely idle. Unfortunately, and even better, we've now halved our memory throughput requirements again because now we've only got to copy into memory from the disk and back out into the network card. So, potentially this doubles our memory throughput. And the marketing materials say, yeah, it's brilliant, you should use this. The reality is not quite so rosy, of course. So the first problem you hit is that real-world internet connections are not perfect, right? There's congestion, there's retransmissions, and these sorts of scenarios are not handled well by the hardware support for doing this encryption process. And so what happens is those retransmissions get shunted back to the CPU to pick up the pieces, figure out what went wrong, and then reset all the cryptographic state in the network card and get it all going again. Now, this is fine. The CPU's got plenty of capacity, right? It's got nothing else to do. But the problem we've got is our link between the CPU and the network card is typically sized very similarly to the link speed of our network card. And this means that without too much back and forth between our processor and the network card to deal with retransmissions, you run out of bandwidth. And of course, your performance then falls through the floor. Now, obviously, there's an option to do some careful engineering to ensure you've got enough headroom and move troublesome traffic around. But again, that's quite a lot of effort to do that kind of thing. But there's actually a much bigger problem, which is we're using Linux on our servers because it's common and easy to find, right? But unfortunately, the Linux implementation of this, unless you're using a Linux distribution that came out within the last month or so, and using some options that almost no one's talking about on the internet, you're going to be paying an extra memory copy anyway, because when Linux loads files from disk, it typically treats them as mutable, and the network card doesn't like that. So the first thing the operating system does after it's read the data is perform a memory copy to put the data into a new buffer that isn't going to be, that can't be modified. This is great for the network card, but of course it completely eliminates the whole purpose of the exercise from our point of view, because we're all about reducing memory bandwidth, and we've now gone back up to 4 trips through memory, back where we started, which is no good. So memory bandwidth is going to run out. Not good. We have another problem, which is bugs. This stuff in Linux, at least, is not very mature at the moment, and certainly my experience has been that deploying this, you end up with things like servers locking up and needing to be power cycled and things like that. So in all, not a terribly happy picture. Now, I work for the BBC, so for the sake of balance, I should point out that actually it is totally possible to make this stuff work and work really well. So you can, for example, work around the problem of dealing with retransmissions and providing headroom by doing the really hard work engineering to steer troublesome clients around that are experiencing lots of traffic drops and making sure you've got plenty of headroom and so on. And it's possible to not use Linux. For example, the folks at Netflix who have been absolutely pioneering the work in this space, they have a team of people working on FreeBSD where they've been putting in the work basically to make this stuff really robust. And so they're having great success with this in production. Of course, in our world, for example, we tend to rely on more typical IT infrastructure for all sorts of reasons. And so as a consequence, this isn't quite on the table for us at the moment. And this is kind of a bit of a problem for many people, I suspect. Now, the final thing I want to touch on is the impact of network behavior. So I'm going to start with a positive example of how the network, how a bit of realism actually helps you. And that is that in the real world, typically when these CDNs are busiest, it's because everyone's watching the Euros or because EastEnders has just come out. It's not because everyone's watching all sorts of weird stuff, odd episodes of Antiques Roadshow from many years ago and things like that. So actually, most of these requests are going to end up being served from RAM. Now, this is immediately removed the need for that copy from disk, and so we've now gone from 4 trips through memory down to just 3. Now, this has a hugely positive impact on the sort of amount of memory throughput available to it. So that takes us up to 340 gigabits a second on the same server. Now that's really nice. Unfortunately, the real world also takes things in the other direction. You can see we're in a very tweaky situation here where just a single extra copy through memory or an extra trip through memory is going to cost you absolutely dearly in terms of your system performance. So one of the problems we've got is our traditional test lab has all of our load generators connected up via 100 gigabit internet connections, or, well, not quite, our pretend internet connections. Now, this being NetUK, I should point out this is not normal, okay? Most people don't have this at home. The trouble is when these machines that have 100 gigabit internet connections request the media is sent and a few milliseconds later it's finished, right? We've done the whole transaction. The real world, of course, the transfer of our media is going to take something like, a number of seconds anyway. And so this whole process gets dragged out over time. And if we look back at our picture here, this causes us some problems because the process of sending this data over the network starts with reading the file in, and at this point we then encrypt it. So we've taken that file, encrypted it, put it into a new buffer, and then sending that buffer off to our network stack to be packetized and sent out and so on. Now, if our entire transmission process completes within a few milliseconds, well, this is all going to happen within the CPU's cache, no problem. But as soon as this stuff starts getting dragged out over multiple seconds, that data, the encrypted intermediate data there, is going to fall out of the CPU's cache and end up in memory. And at this point, we're now up to 6 trips through memory for the same work. And so you can start to see how actually this is going to seriously tank our performance, because now we're going to have to divide our 1 terabit by 6 rather than by 4. So this is unfortunately where actually the towards in the title of my talk starts to bite, because this is essentially the sort of the next steps really, is to try and get this whole process tuned up so that we can modify the way that Linux schedules this work to ensure that data is only requested at the very last second. And this is a bit of a mind shift from like how things are traditionally done, where you try and process things in nice big chunks to avoid the overheads of stopping and starting. But actually in our case, it's not the CPU that we've got a problem with, it's the memory bandwidth. So chopping this stuff into smaller pieces is essential. So that's some of the place where this work is going. The other problem we have is that actually just modeling this stuff is really, really difficult. So as a bit of background, for those of you who don't know about Linux's TC facility, it essentially allows you to emulate all sorts of network conditions. It can do things like adding delays, adding packet drops, and in our case in particular, can do things like limiting your network link speed. And in our case, what we're doing is we're using this to simulate more realistic internet connections for our simulation, our test bench. And this is actually another problem, because our test bench has, each of these machines is pretending to be tens of thousands of people, and actually the TC infrastructure doesn't really scale up this well. So this is again a place where more work is needed really to try and actually just recreate the real world in a lab, to actually even measure this stuff, to be able to optimize it. For those of you wanting to get into TC, the official documentation is rubbish as a new user. this blog post is absolutely outstanding and does all of the like what, when, why, and how, and all that will get you started. So make a note of that link if you're interested. So I guess to finish off really, first thing is the ARM CPUs, they seem to work really well for this workload. This ability to have larger pay sizes is a very easy win. And that's an architectural feature rather than anything a particular vendor has done. But the problem is now we're in this world post-CPU being the bottleneck. It's all about memory bandwidth. And this is a terrifying situation because actually, as you've seen, just adding a single memory copy or adding or removing a trip through memory can have a huge performance hit or benefit. And so you're now into this region where the tuning is not just a nice to have, it's completely essential to even get in the ballpark of the performance you need. And so I guess the final point really is that, we're starting to see 400 gig and beyond network cards appearing and so on. And these things will absolutely sing in the sort of high performance computing sort of environments where the network is all well behaved, all the clients are well behaved. You'll absolutely be able to saturate those things. In an internet environment with realistic real world conditions, it's a lot more challenging. So I guess that's kind of all I want to say. Thank you very much, and any questions?
I know we've got at least one from Slack.
So. Me again. I am aware, although I know very little about them, that there are now smart NICs and DPUs and bits of hardware which are specifically for the purpose of flinging data at the network faster. Have you experimented with them at all? Have they been useful?
Yeah, so we've had a play, although for other purposes actually, and in this case it's not super clear that they solve the problem we necessarily have. Now, I don't know enough to be sure, but it sounds like the very latest generation of these can allow you to do some of the picking up the pieces role inside the smart NIC, and I suspect that gives you a benefit because now you're sharing sort of a much closer connection with the network card inside that smart NIC CPU. But actually in practice the underlying feature that makes this go is the same in the smart NICs and on the not smart NICs. So that's kind of the same.
Okay, I've got a question from online. It comes from Chris Hills. And to paraphrase it with his permission, CGNAT and other IP translation mechanisms are becoming more and more common, but they increase latency for the end user. Do you have any update on IP version 6 support for BBC CDNs?
I'm not working on it, but I know people are. So I think there's some good stuff happening there. The BBC, of course, uses a range of third-party CDNs as well. So the CDN, the in-house CDN I've been talking about here, covers a certain portion of our video traffic, but other things come from elsewhere. I don't personally know the details of what's happening, but I know there's certainly the will. I don't know whether there's where the progress is.
Hi, Jonathan. I'm Andy from Ask4. That was a great presentation. Thank you. There's a possible scenario in the future where everyone still gets to watch EastEnders and the Euros, but you don't have to serve the content yourself at all in the form of open caching. Is it something that you're considering or looking at and might be trialling, and have you got any R&D experience with it?
So I'm not aware of it, and that doesn't mean it's not happening. Unfortunately, there's a lot of stuff going on that I might not know. So I'm really sorry, boring answer, don't know, but maybe.
Hi. Oh, I'm way too short for this mic. Thank you for the presentation. It was really, really, really interesting. Just as a little curiosity, you said that stuff like having to load stuff into memory for encryption, it slows things down, and then slow client connections is even worse. How are you affected by delivering this content through the Tor network? The BBC delivers huge amounts of content through the Tor network, which is a fantastic thing, but presumably that scuppers pretty much everything you're doing here.
I'd imagine it does. I mean, so again, this is probably out of scope for the CDN that we run, which is primarily targeted at UK internet users rather than people abroad and over unusual internet connections like Tor. So this is happily out of scope because, as you say, sounds hard.
Yeah, again, very good presentation, David Gethings. I was wondering if I didn't hear anything mentioned about eBPF. I was wondering if you looked at that and were exploring that. with the issue with the kernel memory.
Yeah. So I've been having a lot of fun with eBPF recently to try and unpick some of this stuff. In fact, one of the big issues with using the ARM hardware is that because it's a, relatively speaking, much less mature platform, the debugging tools for performance debugging are kind of not there. And eBPF is absolutely essential. It gives you the magic X-ray vision you need. For those of you who haven't used eBPF for performance debugging, have a look for BPF trace on the internet later. You'll find things you can do in a one-liner that you would never believe were possible. Never mind things you could do in a one-liner. It's cool stuff. Okay, thank you very much.